Hey guys, I got a request from a student who is asking for a video to help explain some of the Khan Academy practices, especially with the scaling vertically and horizontally. So that's what we're going to look at this video for. Just want to also let you see my beautiful face, let you know I'm missing you guys very much. And I hope you guys are doing well. If you need anything, please let me know. And as we know anything, we're always going to let you know too. Okay? So I'm thinking of you. Today, this video particularly is going to be about the Khan Academy practices about scaling vertically and horizontally. We'll do both of them in this one video, and I'll walk you through some of the practice problems, but realize that I have it set that everyone's seeing some different practice problems, so yours might be slightly different than mine that you're going to see. I'm going to go through the range of what I see for all four of them, and if we need to, we'll do another follow-up video with some other examples. All right. And then they also asked for some information about the even and odd function practices as well. So we'll have an upcoming video about those too. So I'm going to flip over on my screen here. So I am already logged into my Khan Academy account. And so please do the same with yours and go to your assignments. You should see one that's called Scale Functions Vertically, like this. Let me just erase my test writing here. So there we go. So I'm in the practice about scaling functions vertically. Now, there are also some videos that you can watch from Khan Academy, but if they're not explaining things the same way that I normally do, they might be just more confusion. So if I'm scaling something vertically, we saw that this is going to have a multiplier out in front of the equation. So I'm just going to put an idea up here that we have talked about it being an A multiplier out in front of the x, right? Because everything that's happening outside of parentheses is what's happening up and down. So we might have an x that's going on in here, and again, inside those parentheses, we might also have some subtraction or multiplication. So we might see something that looks like this, that might have a multiplier inside. That is going to make a vertical shrink or stretch, and we can do all kinds of playing about moving things around here. And I realize I'm like falling off the screen that you can't see what I'm doing. That's okay. But what we're looking at is this multiplier that's happening out front, and that's what's going to make a vertical change happen. In this case, this is something that would stretch it twice as tall. Because anything outside the parentheses away from the x's happens just like we would expect it to. So here we have a function g is vertically scaled version of function f. We are starting with f, the blue one here. F is solid, g is dashed. And so we are starting up here at 16. And what it's doing, it's the same input. We still have our input of x equaling 4, so we're not changing the inputs on this. And we can tell because they've put these dots here that show us that we are starting at 16. Oh, I really miss my tablet where I can write a little bit more easily. I have to do this all with a mouse. It's really weird because I'm left-handed. So we start up here with an output value of 16, and by the end of whatever it is that we do, we are ending down here with our end point at 4. And so if I start at 16, and I have some kind of a scalar factor for 16 that then gives us the end point of happening at 4, then I need to think about what is that a value that I would have to multiply 16 by to get to 4. So our starting point here at 16 to end at 4. You may already be thinking, hey, to get that a by itself, that scalar factor, we're going to have to divide both sides by 16. And so my scalar factor that I'm looking at is going to be 4 over 16, which we can simplify to 1/4. Okay? So what it's doing is it's making it 1/4 the height. So it's taking every single point and cutting it down by 4. I can also double check this here because I see this point here that's happening at 4. And at my same input x of 2, it's taking that 4 and it's squishing it down to a value at 1. So it's taking 1/4 of the size. So I'm looking for a function that's going to show that it has that 1/4 multiplier out front. And so as I scroll down and look at my answers, I see that multiplier is happening right here, that g is 1/4 the height of f of x. So I'm going to tick that one and check my answer. Ooh, that was pretty loud. Sorry about that. And we got it right. So let me turn that volume down a little. Oop, that's turning it up. All right. Next time it shouldn't be that loud. All right, so let's see what our next question is looking like. Here we have a graph of a function f, and g is defined as twice as tall as what f is. So I'm going to take every single output that is here, and I'm going to make it twice as tall. Now, when we're stretching it vertically, it's important to know that a vertical stretch locks in our zeros right where they are, because our output is 0. Our y value here is 0, and anything times 0, whatever scalar factor we use, is not going to have any impact on that at all. So those two guys are locked in right there. And so if I want to think about something that is going to be stretched twice as tall, what I'm seeing is that my new g at, and so my input value here, my x is -3. So g of -3 is going to be twice as big. I'm going to take that 2 here. Twice as big as what my f at -3 was. So my original function at -3, follow it down, follow it over, is at an output value of -2. So I'm taking that point at -2, and I'm going to stretch it twice as far, which means instead of it being at -2, it's now going to be at -4, because I'm stretching it twice. 2 times -2, -4. So it's going to have a point down here at -4. So it's still going to then go up here, and now it's going to stretch taller when it gets positive like that. And so we see a vertical stretch happening something like that. So I'm going to look for a graph that has at -3 for an x value, an output value at -4. So I see an x value at -3 and an output at -4. That one works. Ooh, this one works too. That one definitely does not work. Okay, so I'm going to put a big ol' X through this. Or wait, I don't want to pick that. It's not right. So let me draw a little whoosh, whoosh. Oh, it won't let me. That's terrible. Okay, so I know it's not C. And I know it's also not D, because this one is making it half as tall, and we want it down at -4. So it's not C or D. I just have to think now, is it going to be A or B? And so I see some other points that are happening here. And these points, we said, are locked in here, so they should be stretching upwards. At our, I'm looking for zeros happening, and so here's our points here. We should have zeros of the graph hitting the x-axis at -5, and here at -1. -1 and -5 is where I'm looking for these zeros. And so when I look here, -1 does not have an x-intercept, and neither does -5. Here they do. There they are, right here and right here. So I can tell that this is the graph that I'm looking for, because my midpoint, the vertex, has dropped down to -4, and I've kept those same zeros, the same x-intercepts. There we go. Let's see what they have next for us. So it looks like another one where we're going to be stretching or shrinking, and we're looking for the equation of it. We have our starting equation up here. So my starting equation, x to the third plus x squared, is the solid graph in blue here. And I'm taking this one point and I'm stretching it up to here. So I start at 2, right? S-T-A-R-T. I really need to get a pen or something like this. I start at 2. I wonder if I could. Alright, maybe that'll work. But I need something that'll... Anyway, I'll try it for next time. So it's starting at -2. I'm sorry, +2. So the output's happening at 2 in our original graph, and 2 times some kind of scalar that I don't know what it is, so I'm going to call it A, gets me a new output at the same x input of 1. That 2 is now stretched up here to 5. And so I need something that's going to stretch it taller. To get that factor by itself, right now it's multiplying by 2, so I need to divide everything by 2. And so we're going to have an A value, a scalar value that's going to make it bigger and taller of 5/2. There's our scalar factor. So I want the entire equation multiplied by 5/2. Okay, so if we put that scalar out in front, because we know what's happening out front, 5/2 times our original function up here, x to the third plus x squared. It might look in a different format, and I can kind of tell that it probably will because of what I saw down below. So I'm going to have to distribute that 5/2 to each term inside. So my first two I'm skipping right away because they're 2/5, and that's not what our multiplier is. Our multiplier, a scalar, we said was 5/2. I'm going to pick D because it's happening for both of our x terms. It's happening outside the parentheses at first, so it's going to impact every x term that we have. And so we have it right. One last question. And so I see that we are still stretching vertically, thinking about this. We have our function up here on top, x squared minus 2x minus 1. And so I need to now think of what is the graph of 2x squared minus 4x minus 2. In comparing these two that I see here, what I'm noticing is that everything has been multiplied by 2. Do you see that? Our x squared multiplied by 2 is now 2x squared. Our minus 2x is now a minus 4x. And our minus 1 is now minus 2. So we took all of our function f, and I multiplied the whole entire function of f of x by 2. Which means everything should be stretched twice as tall as where it is. Now remember, this means that we're going to lock in our x-intercepts. These two guys are exactly the same. We are not changing when it's a 0 because our output, our y, would be 0 here. And 0 times 2 is 0. So it's still going to be zeros. So I know for sure that I need a 0 at -1/2. Zeros at -1/2, it looks like, and about 2.5. I also know that this vertex point, this lowest point, is going to be stretched twice as far. So right now it's at, if I look at my scale, it's at a -2. And so it's going to stretch that vertex down here twice as far to a -4. It's going to stretch my positive outputs up here, like I have one here at +2. It's going to stretch that output up here to +4. And same thing over here. It's going to stretch this output here that right now is at 7. See where it's crossing the grid line right here? And it would make that like 14. So I'm up off the graph at this point. Okay, so I should be looking for something that has this kind of parabola shape to it with zeros at -1 and 2.5. A vertex down at 1, -4. And these few other points. So I'm really going to be looking at these key points first to see which ones fit this graph that we have that's twice as tall. So I'm looking for zeros at -1/2 and 2.5, and I'm also looking for a vertex at 1, -4. Let's see which ones match this. My vertex here is on the x-axis. That's definitely not at 1, -4, so I'm going to skip that guy. This, again, the vertex is at 1, -1, not -4, which is where I need it. So I'm going to skip that guy. Here's a vertex at 1, -4. That's looking pretty good. And when I go check my next spot, my zeros are at -1/2 and 2.5, so that's looking good. And the two marked points that we have are up at 4, which if I look up here, yep, those things should be up at 4 with those two marked points that they gave us. C is looking really promising. D is at 1, -6, so that cannot be right. It has to be C. And we are perfect all the way through. Okay. So you can show your summary. You can see how they did it. They do a whole step-by-step. Remember, you can always get a hint down there. But we got this. And you can keep on practicing, and you can do it again, and it should have some different questions. So if you just come over here and click again that you want to practice, it should be giving you some different ideas, right? Keep going, keep growing, they tell you. So you can have a chance to get some more practice if you go in and do that again. Right? Go to your assignments page. I'm going to skip down, though, to the practicing scaling functions horizontally. So I'm going to my next assignment. For me, it's showing up in my side column over here, but this way it's also up there. Let me hit pause for a second. Can I hit pause? Where's my pause button? Ooh, yeah. All right, sorry, back again. I went to go get a pen to see if I could get a little stylus, but it wasn't working. Anyway, so here we are now. We're going to scale functions horizontally this time. This means left and right. And so this is where we're going to start seeing some functions that are going to have scalings going on inside the parentheses with the x. So we'll start seeing some f of and some kind of scalar or something that's going to be going on inside the parentheses with our x values. This means we're changing the inputs. Okay? So a way to think about it is that if I had an input that was at 20 and I'm stretching something so it's twice as big, right? Something that's going to be a lot bigger, right? My new function is going to have that input at 20 is now going to be at 40 if we're stretching it wider. Okay? But remember, though, that might mean that my new function, if I'm thinking about g, that new input at 40 if I want to see where it is at 40, it's going to be that old function with the same value, but it was showing up at 20. So notice that it's going to be cutting it in half. Remember, this is the one that's going to go kind of opposite of what we think. Just like everything that's been in our parentheses, it goes opposite of what we would first expect it. Okay? So if I need my new input at 40, that means it was my old input at 20, but in order to get to that 20, I need half of that 40 input that I'm looking at. Okay? So keep on remembering that this now is what's happening inside. Everything inside the parentheses is moving left and right. That includes if we are adding or subtracting a number, or if we have a negative in front here that's going to be flipping it. It's going to be doing our horizontal reflection. All right. Now they give us some points here always to help us kind of focus into something that might be interesting and important. And because now this time we are looking at a multiplier on our x, when we have these scalars going on, our y-intercept is the one that's locked in place. So when we had a horizontal stretch or shrink, our x-intercepts were the same. Here, our y-intercept is locked in. So I see this thing that has a y-intercept that's at 0 at the origin. So any graph that I'm looking at, although I'm not comparing graphs here, Any graph would also have to have that origin there. What I do see that we're doing is we're taking our starting point here that was at 4 of our input, because we're scaling our inputs now. So what was at 4 is now happening at 8. All right. So we think about where we are and how we're going to get there, right? So our G at 8, looking at this guy here, is our f function with some kind of scalar, but we still have to have that 8 going on here, all right? Our x's have to be the same. And so we're multiplying it by some kind of scalar that's happening here. And I don't know what that scalar is, so I'm just going to call it letter C for right now. Okay. So what has to happen to that same input to now get it from our new one? Remember, it was at 4, so we need something going on so that this will equal 4. It was our old f of 4 function, right? That's where our point was. So it was at f of 4 started. We're doing something to it to get it to now be at 8. And so when I think about this multiplier, C times 8 with our new guy, but I want it to equal what was the old 4, I can see that what I'm actually needing to do is I'm needing to cut that 8 in half. Okay. So maybe you're thinking, okay, I know where my new one has to be to match my old one. I need to divide both sides by 8 to get that C multiplier by itself. And so C would equal 4 over 8, which is the same in our world when we simplify it as 1/2. So I'm looking for something that's got a 1/2 multiplier inside here, our f of x times 1/2. And when I look down, I see it's happening right here in B. It's half, it's cutting all of the new inputs, the new x's that we have match up with half of the old inputs, right? So it's kind of a strange way to think about it. Half of that old input. So even though it's being stretched twice as wide, it is a half multiplier. Let's see if we got that right. Looking good, looking good. All right, so we're going to keep on thinking about, hey, where am I going? What do I need to be from the multiplier on my new number compared to my old number? We're going to keep on doing that same idea, okay? So my new number compared to my old number, what this is telling me, it looks like it should be 4 times bigger, but what it's telling me is it's actually going to be 1/4 as wide. This is what I mean, that everything in parentheses is happening opposite of what we think. It looks like it should be 4 times wider, but really it's 1/4 as wide. So our inputs, if we're trying to find out where this new 4 is going to be, right? So our new G of 4 is where our old So here's that 4 that's happening, where our old 16 was. Now I've fallen off the graph at this point because my 16 is like way up here. And it would be bringing it over here to 4. So let's try it a different way. Right? If I know it's going to be 1/4 as wide, my point that's going on here, remember this point's going to be locked in. Our y-intercept is locked in. This is not changing because our x at this point is 0, and 0 times anything is still going to be the same. So our vertex here is locked in at a 0, -4. Any y-intercept in these is locked in. Okay, but what it's going to do is from there it's going to bring everything either closer to the y-axis or farther away from it. So we still don't have our other new point that we have going on. If we know it's going to be a fourth as wide, what is showing up at this 4 point at 4, 0 is now going to be showing up at 1, 0. It's a fourth as wide. All right. So I need to know like what that new input is. Here's where we're going to think about that. All right. So what I'm thinking of is that a way to remember that is that my G at some number is going to be the same as my F times that same number. Okay, so that's a multiplier in there. Sorry about that. So G of some number is F of 4 times that same number. So if I want to find like G of 2, it would be the old F of 8. So this F of 8 is now just going to slide over here and be the new 2. Okay, because my G of 2, if I put in 2 here, I have to put in the same number for the same question mark. So if I want to figure out where that 4 coordinate is, that x-intercept that is happening at 4, that would have to be 4 times 1. That's where that intercept is happening. So that means that new intercept is happening at G of 1. This number has to match. Alright, so I should see a super duper skinny, oh that's a terrible straight line, a super duper skinny V-shaped graph going on like here, with my vertex still at 0, -4, and everything squished in skinnier. So vertex at -4, vertex at -4, vertex at -4. Ooh, this guy totally out. Not at all right. And I should be seeing my x-intercepts are squished in now at 1 and -1, because what was at 4 is now happening at 1. So that's going to match this graph here because it's between 0 and 2. Got it. Keep on going. This one we see a squish is happening. Again, notice that the y-intercept here is the same. It's locked in. So our same before and after. And so what we have done now, f of x is the absolute value of x plus 2 minus 2. So it took something that normally an absolute value graph is at the origin, and it goes up in a V shape like that. That's what an absolute value graph looks like. This one has taken it and has moved it left 2 units, L-E-F-T, P-L-U-S, boom, boom, and has slid it down 2, boom, boom. Okay, so our f function, our starting function, is in blue here, the solid line. And took our standard absolute value graph and moved it over and down 2, and so that's why its vertex is here. Okay. Now what I see that this thing has done is that it has squished our graph. And if I'm looking only at horizontal shift, what I'm seeing is that now what was another intercept at -4 has been squished into -2. What was happening at -2 is now happening at -1. So that multiplier, that thing, that -2 is still happening at the end. That's why they all have a -2 still, right? We're not changing our outputs at all. We're only sliding all of our x's. We're squishing the graph so that it's half as wide. Half as wide. And so you may be reminding yourself that that means everything is going to be 2 times bigger inside with the x's. Okay? So everything's going to be some kind of multiplier of 2. Right? All of our x's that we see, we're just going to have a 2 multiplier right in front of that x. Everything else is going to stay the same. Right? Because we don't want to keep on sliding it or change how we're sliding it side to side. We just need to change that input. All right? Alright, so what was at -4 is now becoming -2. It's half as wide. That means it's a 2 times multiplier. Okay? So, when we think about this idea about if we need it to be the same point that we were seeing at -4, is some kind of multiplier happening that now brings us to a -2. Okay, so our new point at -2 has to have some kind of a scalar that got us to the old point of -4. So really we need to take every x and think about it as half as much, but that means we're taking the original and we're multiplying it by 2. Okay. So what is happening here at -1 in our new one was happening at -2 before. It was at twice as large. So it should be this 2 multiplier happening here in front of the x. Everything else is staying the same. Yes. One more to go. We have another absolute value graph, and it's been slid down 8 units. Our new graph is going to definitely, because we're only doing a horizontal scale, this guy is still going to happen at 0, -8. Our y-intercept is still the same. I better see a vertex at 0, -8. Everything else is just getting either sucked into the y-axis or pushed away from the y-axis. Okay, so I can already eliminate A. B is still in contention, C is still possible, D is still possible. The difference now that I'm seeing when I look at my next part is that I'm going from an x to a 4x. Normally making something 4 times bigger would make it think that we're 4 times wider. This is going to be 1/4 as wide. Okay, 1/4 as wide. So my new something, my new g of something, is my old f of 4 times that same something. Okay. So my old one that was at 8, alright, so I'm looking at this point here at 8. My old f of 8, oop, it won't let me draw that low. My old f of 8 is going to be my new thing, but it's got to be 4 times something. Okay, my old f of 8. That 8 has to be four times So normally we'd be looking at this thing and it would be 4 times 2 is what equals 8. So my new point is going to be at 2. Alright. That question mark has to be a 2. So if that helps out, thinking about where you had a locked in point at 8, It is now the same as been with that scalar. It's 4 times something. We need to find out that something to find out our new something, and our new something is here at 2. It's going to be a fourth as wide. Okay, so we're looking for something super duper skinny with those points at 2, and I'm seeing them happen here. Here it looks like they're at 4 and -4. Here they're at 2 and -2, and again we still have that vertex at -8. Hopefully that was helpful. Going through a couple examples together. Keep practicing, alright? This stuff's not easy. And when we start putting it all together, it's going to be even more confusing because there's all kinds of stuff going on all at the same time. Okay? Hang in there. I'll make another video, but enjoy for now.